So first I will speak on what we have not discussed today morning. Today morning we just started this, we started kinetic theory of gases, and because of the network problem we could not complete that. Therefore, now I will make the presentation in which I would like to concentrate on the behavior of gaseous molecules for some time, and after that I will give another presentation in which I will discuss the biophysical chemistry what we discussed yesterday. First, we are going to see the gaseous state. So this is what we have seen today morning. Okay, look, there are three states of matter. So gas is a substance whose boiling point is below room temperature under atmospheric pressure. Similarly, liquid is a substance whose freezing point is below room temperature under atmospheric pressure. And a solid is a substance whose melting point is above room temperature under atmospheric pressure. Now you should try to understand the differences among the three states, namely gaseous state, liquid state, and solid state in a scientific manner. When you discuss the definition of a gas, we speak about the boiling point of the liquid. Because below the room temperature, it may exist in the liquid state. That is why the definition says like this: gas is a substance whose boiling point. You may ask, a gaseous substance may not have a boiling point, but its liquid part has boiling point. Therefore, whose boiling point is below room temperature means at room temperature, certainly that will be existing in the gaseous state. So gas is a substance whose boiling point is below room temperature under atmospheric pressure. And a liquid means liquid has come from a solid state. So solid melts to give liquid. Therefore, the liquid's freezing point should be below the room temperature. Therefore, at a room temperature, everything will be in a molten state, that is a liquid state altogether. Therefore, liquid is a substance whose freezing point is below room temperature under atmospheric pressure. So for a solid state, that has to be solid, that should not melt away. Therefore, the melting point should be above the room temperature. So solid is a substance whose melting point is above room temperature under atmospheric pressure. So these are the definitions for the three different states in which the matter exists in the world. So what is a matter? Matter is anything which occupies a space and has a mass. It should have mass and it should occupy space. That is a matter. Then what is mass? Mass is the total quantity of a matter. What is matter? Anything which has mass and which occupies a space. If you take a water system, water, the frozen water is ice, and the water, the vapor water is steam. At 100 degrees centigrade, it is vapor. But at 0 degrees centigrade, 0 degrees centigrade is the melting point of ice. When you take an ice cube and put it in the 0 degrees centigrade, and you can see the melting of the ice and the water coming out, and also you can see the water vapor going up. Therefore, water exists in all these three states at 0 degrees centigrade, 1 atmospheric pressure. So these three states of one particular substance can coexist. So water, the vapor water, the liquid water, and the ice, they coexist at the 0 degree centigrade. Now, look at this. What is the differences? What are the differences among solid state, liquid state, and a gaseous state? In solid state, the molecules are in fixed position and the molecules are very rigid. They cannot move here and there. It is because of the very strong attractive force existing between the molecules. As the molecules are tightly packed and the molecules are rigid and they are all fixed in their position, there is a little space in between them, or practically we can say no void space. Void means empty space. No void or little space between the molecules in solid state. It doesn't mean that there is no space at all. Actually, interstitial sites are seen in crystallographic understanding, but comparatively, there is no void or little space between the molecules in solid state. Therefore, there is no significant rotational and translational motions. But the molecules have a vibrational motion. But rotational motion and the translational motions are not found in the case of solid state. Then you may ask what is rotation and what is translation. Translation means a molecule as a whole going here and there. That is called a translationary motion. Rotational motion means about its dipole moment it returns. That is rotational motion. So vibrational motion means suppose two atoms are bound together by a bond. The bond will stretch and bond will compress. Bond will stretch and compress. This stretching and compressing or bending or scissoring or rocking, these are all the vibrational motions. But in solid state, rotation and
Sir,
translation are not found.
sir,
Yes,
sir, screen தெரிய மாட்டேங்குது சார்.
in the screen. Oh, okay.
சார் இந்த
Okay.
ஸ்க்ரீன் ஷேரிங் அப்படியே தான் வருது, ஸ்க்ரீன் தெரிய மாட்டேங்குது.
என்னாச்சு தெரியுதப்போ?
இப்போ தெரியுது சார்.
Okay, right. Okay. So in the solid state, the molecules are rigid. They are fixed. They have a strong attractive force. Therefore, a very little space, wide space is found. Therefore, no significant rotation or translation. But vibrational motion is found. And also solid substances have a definite shape and a definite volume. These are all the characteristics of a solid state. And taking the liquid state, they are not so rigid as the solids. And the attractive force among the molecules in liquid state are also not so strong as in the case of solid state. Therefore, they do not have a definite shape. They assume the shape of the container in which they are taken, but they have definite volume. So the definite volume is there. Therefore, there is a little more wide space when comparing the solid state. Therefore, translation motion is also possible. Vibrational motion is also possible. Rotational motion also possible. And moreover, compression is possible. Compressing a solid state is almost impossible, but a liquid can be compressed. Compression is possible. That is why solids and liquids are called condensed phases. Phase means a uniform system having a well-defined boundary. That is a phase. Liquid is a phase. Solid is a phase. But solids and liquids, they are altogether called condensed phases. They form condensed phases because the molecules are very closer. The molecules are very closer. In solid state, they occupy a fixed point and the molecules are very rigid. But in liquid state, they are very free to move here and there. And the attractive force among the molecules in the case of liquid state are not so strong as in the case of solid state. Therefore, the molecules in liquid state experience a translation motion, rotational motion, and vibrational motion. And also, we can compress the liquids, but the compression is very small. But you can compress. Compression is possible in the case of liquids, but the compression is not possible in the case of solids. But when you take a gaseous state, the attraction between molecules are very weak. That is why a large wide space is found among the molecules of a gaseous substances. And also the translation motion, rotational motion, vibrational motions are well seen. And moreover, apart from this, there is a random motion of molecules in all directions. and also the density is very less, and also the compressibility of gaseous substances is very high. That is why they do not have a definite shape and a definite volume also. They will fill almost all the volume of the container. Say for example, suppose in a closed room, you take a fragrance material and you are simply spraying the material, just 100 molecules are coming out of the spray. These 100 gaseous molecules will try to fill the entire volume of the room because they do not have a definite volume. That will fill the entire volume of the room. So similarly, if suppose if you are taking a balloon, you are blowing the air into that, the balloon expands, which means that actually why the balloon expands. The gaseous molecules are in a random motion and they are moving here and there and they are colliding with each other. They hit on each other. At the same time, they hit on the walls of the container. They are all continuously hitting on the walls of the container. So this hit, their collision on the walls of the container altogether manifest in the form of pressure. That is actually the pressure. What is pressure? Pressure is the force, the hitting force of gaseous molecules on the surface. So pressure is a force acting per unit area. What is the number of molecules hitting on the wall in a unit area? That is the pressure. When pressure increases, when more number of molecules hit, pressure increases. Or when the molecules hit with a high kinetic energy, the pressure increases. That is why pressure is directly proportional to temperature. Because when you raise the temperature, you are not increasing the number of molecules which hit the walls of the container, you are increasing the kinetic energy of the molecules. So the molecule now they are getting speeded up and they are getting accelerated due to the kinetic, due to the increase in the thermal energy, and with a high kinetic energy they hit on the walls of the container, which consequently increases the pressure inside the container. So these are all the differences among the solid, liquid and the gaseous state. Suppose if a question is asked, you write down the differences among the solid state, liquid state and the gaseous state. You should not present as you have studied in lower classes. That should be more scientific in approach, because in schools you might have not studied the idea about the void space, the idea about the translation motion, vibrational motion, rotational motion. These ideas were not given in schools. So here the discussion has to be a little more interesting and a little more scientific and a little more enlightened. So you should write in your own language the differences among the solid state, liquid state and the gaseous state. So now, next listen here. So the gaseous molecules or the gases, they have very peculiar behavior, very peculiar behavior. And I have already told you one simple example. The gas molecules will try to fill the entire space in a container. They fill almost all the volume. That is why we say that they do not have a definite volume also. So why the gases have this peculiar behavior? This peculiar behavior of the gases is due to the negligible attractive force between the gaseous molecules. The gaseous molecules attract each other, but the force of attraction between them is almost negligible. That is why the gas molecules are able to move far apart. They are free to move in all directions in a zigzag motion. They are all moving. And also there is a large wide space, empty space between the molecules. One molecule is here, another molecule is here. In between the molecules, there is a large volume of wide space. So these are the two reasons behind the peculiar behaviors of gaseous molecules. Now, before going to the kinetic theory of gases, there is a fundamental laws you should understand. The first law is Avogadro's law. According to Avogadro's law, volume is directly proportional to number of gaseous molecules when temperature and pressure are maintained constant. When temperature and pressure are maintained constant, volume is directly proportional to the number of moles of gaseous molecules. If we have a large quantity of gaseous molecules, the volume will be more. If we have less quantity of gaseous molecules, the volume will be less, provided the temperature and the pressure should be maintained constant. That is Avogadro's law. Second one is Boyle's law. According to Boyle's law, volume and pressure are inversely related when number of moles of gases and temperature are maintained constant. Suppose you take a balloon, you are compressing the balloon. When you compress, volume decreases, therefore pressure increases. Suppose if you want to increase the pressure, you have to reduce the volume. Similarly, if you reduce the pressure by expanding the gas, volume increases, pressure decreases. Therefore, volume and pressure are inversely related when temperature and number of moles of gases are maintained constant. According to Charles' law, volume and temperature are directly related. I have already told you, when you raise the temperature, what happens? The gaseous molecules gain more thermal energy, and because of the thermal energy, they get more kinetic energy, and because of the kinetic energy, they move fast. And because of their fast motion, they hit on the walls of the container. Therefore, the pressure increases. If a container is expandable, what will happen? In order to maintain the pressure constant, again the volume will increase. Therefore, on rising the temperature, pressure also increases, volume also increases. If you maintain the volume constant, pressure increases. If you maintain pressure constant, volume increases. That is what is the idea. See, volume and pressure are dependent parameters. When you maintain pressure constant, volume increases with the temperature. When you maintain volume constant, pressure increases with the temperature. That is Charles' law. Now I am going to combine all these three laws, combining the above laws. So volume is inversely proportional to pressure multiplied by temperature multiplied by number of moles of the gas molecules. I suppose you understand what I have written here. So volume is directly proportional to temperature and the number of moles of the gas and inversely proportional to pressure. So this P can be brought this side. Actually, this kind of exchange should not be done for proportionality, can be done only in the case of equation. So only in the case of equation, this P can be brought to the left hand side. You should not do with the proportionality, but you can do when a constant is introduced. Therefore, PV is equal to a constant into number of moles of the gas into temperature. What is the number of moles of the gas? Is N by N0, which means N is the number of molecules. Number of moles means N by N0 means the number of molecules divided by Avogadro number, N. Therefore, N is proportional to N. Therefore, that can be replaced. Therefore, PV is equal to nRT, where R is the constant. And that the constant is called the universal gas constant. So PV is equal to nRT is the ideal gas equation. This is how the ideal gas equation has been derived. Now look here. You should well understand the nature of R. R is universal gas constant. What is universal gas constant? You know PV is equal to RT. So R is equal to P into V by T. You know what is P? P is a pressure. The unit is force acting per unit area. What is pressure? It is the force acting per unit area. What is volume? Area multiplied by length. So I am substituting these two things in the place of pressure and volume. So when you substitute, finally you are getting, because this area and this area, they are getting cancelled in this equation. And what you are finally getting is a force multiplied by length divided by temperature. Force into length is nothing but work. Newton meter, work. So many Newton, so many meter, Nm, which is the work. So I can write R is the work done per degree. Actually, these equations are derived for 1 mole of the gaseous substances. Therefore, I can write per mole. Therefore, it is R is given the unit work done per degree per mole. And in the lower classes in the thermodynamics itself, we have seen what is gas constant. No, we have seen the heat capacity of the gas at a constant volume and the heat capacity of the gas at a constant pressure. And when we subtracted the heat capacity of the gas at a constant pressure and minus heat capacity of the gas at a constant volume, we got the R, which is universal gas constant. So you should be able to relate things. We are studying the kinetic theory of gases, and in the second year we have studied thermodynamics, and in the first year we have studied inorganic chemistry, and all these things should be interrelated, and you should have an overall idea. You should know the link between the various subjects, then only you can understand. The same R, universal gas constant, what we derived in the thermodynamics is derived in a different fashion here in the gaseous state. There we derived as the heat capacity of the gas. What is heat capacity? It is the heat energy required to rise the temperature of the body by 1 degree. But what we say here, it is the work done per degree per mole. The same definition, but in a different view. Therefore, the R can be expressed in various units, like it is 8.314 joule per Kelvin per mole, or 1.987 calorie per Kelvin per mole, or 0.08205 liter atmosphere per Kelvin per mole, or 62.363 millimeter of mercury into liter per Kelvin per mole. So these are all the various units in which the R can be expressed. Any doubt? So finally, in the gaseous state, this is the last thing I'm going to discuss in the gaseous state. Look here, for today's class, what is normal pressure and normal temperature? Normal pressure means 76 centimeter of a mercury column. Actually, in our chemistry department, in the HOD's room, there is a barometer, which is a very old barometer. When the college is reopened, you can make a visit, which is more than 150 years old barometer, still working perfectly, and still you can note down the atmospheric pressure and the room temperature using that barometer, still working perfectly. There you are able to see a mercury column. Actually, the construction of a barometer is very simple. You have to take one side closed, a long glass tube, and fill it with mercury, and then close the open mouth with your thumb, and then you have to invert that into a beaker containing mercury and open. That's all. Now the mercury will come down, creating a small vacuum at the bottom. When the vacuum pressure and the pressure acting on the mercury in a beaker, they are equal, that is the level. Actually, if you measure that level from the level of the mercury in the beaker to the level of the mercury in the tube, that will be exactly 76 centimeter or something. So 76 centimeter mercury is the normal pressure. Normal temperature means 0 degree centigrade, which is equal to 273 Kelvin. Accurately saying, it is 273.15 Kelvin. So now what is pressure? Look here. The pressure exerted by the mercury column is height 76 centimeter, rho density 13.60, g acceleration due to gravity, which is 981 dynes per centimeter square. When you multiply all these factors, you are getting 1.0135325 into 10 power 6 dynes per centimeter square. That is the unit of pressure. Suppose if you want to substitute in SI units, 0.76 meter, 76 centimeter is substituted as 0.76 meter. 13.60 is the density, and 9.81 meter per second square is the acceleration due to gravity. When you multiply all these things, pressure, you are getting 1.014 into 10 power 5 Newton per meter square. So this Newton per meter square, so this is the pressure. So you can say normal temperature pressure or standard temperature pressure. So 1 mole of a gas at the normal temperature pressure or standard temperature pressure, 1 mole of a gas will occupy a volume of 0.0224 meter cube or 22.4 liter. If you take 1 mole of any gas and fill it in a container, it will fill at a normal temperature and the pressure, it will fill a volume of 22.4 liter. So these are fundamental ideas you should always remember. Only with these factors you can do the calculations in gaseous state or in thermodynamics. So what is normal pressure? 76 centimeter or 0.76 meter. What is normal temperature? It is 273 Kelvin. What is normal volume? That is the volume of 1 mole of a gas at a normal temperature pressure condition. It is 22.4 liter or 0.0224 meter cube. So these are all the fundamental ideas in gaseous state. Now I stop the presentation and I think we end the meeting and restart the meeting.